So we come to calorimetry. Calorimetry is essentially an experiment which is performed inside a calorimeter, which is this object shown here. You do not need to know the diagram. The only thing you really need to know about this is it provides a well-insulated way of isolating the system inside so that two things can interact, two or more substances can interact with each other without having to interact with the environment. So it isolates a system. So you can measure the energy lost from something and how much energy is gained by other things without having to consider the environment, okay? And you can see that that's exactly what we need to do to measure specific heat. We need to feed a known amount of energy into a known amount of substance to see the change in temperature produced, yeah? So we can provide analysis, do analysis based on calorimeter experiments, and the conservation of energy will apply, right? All the energy that comes out, let's say you have just two substances in there, then the energy that comes out from one must have gone into the other. There is no other place for it to go. Therefore, the energy that comes out from the warmer object, say negative Q hot, is going to be all the energy gained, which is negative, and which is positive Q cold, yeah? Okay. So the sum of all the energy changes must be zero by conservation of energy, okay? If you have more than two materials, then sometimes it's hard to know which material lost energy and which ones gained, right? But you can always apply this formula, provided you are consistent in using Q equals MC delta T, where delta T is always TF minus TI. Then the sign of this term, delta T, will help determine whether an object gains energy or loses energy. But in your particular case, you'll only ever get two materials in this course. Therefore, you don't have to be very careful with this. But if you had more, you would always have to be careful about the signs. Okay, so let's do a problem on this. And I'm going to need to write here. So 125-gram block of an unknown substance with a temperature of 90 degrees Celsius is placed in a styrofoam cup containing 0.326 kgs of water at 20 degrees Celsius. So here's my water in the cup, and this is the amount of water at 20 degrees. This is the block that's going in. It's of an unknown substance, so we don't know its specific heat. I'm going to write S for the substance. We know we have 125 grams of it, and it's at 90 degrees. Yeah? So this is my sketch. The system reaches an equilibrium temperature of 22.4 degrees Celsius. So that tells us that this block is going to lose heat, right? And the water is going to gain heat. So we can determine how much heat is lost by the substance. This is actually going to be negative of this, right? So T final minus T initial, I should have written this, 22.4, which is the final temperature, minus initial temperature, which is 90. And that gives you negative 67.6, yeah? What about the energy, the temperature change for the water is going to be 2.4 degrees positive, yeah? We can see that. And then we're going to, what's the question? What is the specific heat, Cx, of this unknown substance if the heat capacity of the cup is neglected? So effectively, the cup is acting like a calorimeter, right? It's just a container where you can have the interaction between just the two substances inside it, and the cup itself does not get warmed up. Okay, so it's acting like a calorimeter here. And the fact that it's open to air also we will neglect, so there's no consideration for that. Then the Q cold, which is MC delta T for water, must equal the energy lost, right? Q hot, which is negative, MC delta T for the substance. Yeah? So this negative sign is going to cancel with this, get multiplied negative, and negative from the delta T here is going to turn positive, right? So then I have no negative signs here. I'm just going to put in all the values I want to solve for the C of the substance, right? So just taking all the values from the question and solve, we get 388 joules per kg degree Celsius. Just be careful of the units, that all the units match up. So for example, the 125 is in grams, therefore I converted it to kilograms over here. Okay, let's look at another question. The number of kilocalories in food is determined, let's clear this. The number of kilocalories in food is determined by calorimetry techniques in which food is burned and the amount of heat transferred is measured. How many kilocalories per gram are there in 5-gram peanut if the energy from burning it is transferred to 0.5 kilogram of water held in 0.1 kg aluminum cup, causing a 54.9 degrees Celsius temperature increase? And then we're given specific heat of water, specific heat of aluminum, and matching units. Okay, so we're going to burn this, and all the energy that comes out is now going to go to heat two things. Yeah, it's going to heat the aluminum cup and the water. So energy is going to be taken up by both of these. We need to add the two Q's here. Q equals mc delta T for water, plus the Q for aluminum, which is mc delta T for aluminum, right? And set that equal to the energy released from burning. So if we add those two, we get the total energy. We need to then divide by the 5 grams because they asked us how many kilocalories per gram. And we're going to get our energy in kilocalories. Okay, so you can proceed and do it and then check your answer against mine. Yeah, here I've added the mc delta T. This is the water. My delta T is here. It's the same for both. And this is for aluminum. Then I divide it by the 5. Yeah? Let's look at one last question. On a hot day, the temperature of an 80,000 liter swimming pool increases by 1.5 degrees Celsius. It's my delta T. It's positive. So heat must be going in. What is the net heat transfer during this heating? Ignore any complications such as loss of water by evaporation. Okay? So we're going to say that the environment doesn't really matter in the terms of no energy is lost to the environment, though energy may be gained from it. Okay? Obviously, the sun is heating the pool. So we need Q equals mc delta T, but we don't have M. Can we find M? If we know the volume of water, we're going to assume that it's pure water. Okay, you're going to use the density of water and the volume to find the mass, yeah? And then you know C, you know delta T, so you can find Q. Do that and compare your answer with mine. There I find the value of M, there I find Q, which is 5.02 times 10 to the power 8 joules. Okay.